Hello, deep learners. We are Project 35 and we are here to present to you membership inference attack. Speaker recognition technology has become increasingly prevalent, especially in security and authentication tasks. However, there is a growing concern about their vulnerability to external attacks such as membership inference attacks, or MIA as we call it. In MIA, the attacker tries to determine whether a specific data point belongs to the training dataset or not by observing the model's prediction on that data point. Our goal in this project is to evaluate the effectiveness of different membership inference methods and assess the vulnerability of speaker recognition models, specifically eKappa, TDNN, and X vectors to such attacks.
So why is membership inference so important? It is important to safeguard user privacy and prevent data leaks from the model, uphold data protection laws, build trust in machine learning models, protect valuable intellectual property, as well as ensure the ethical development and deployment of all machine learning models. Now, how do we do membership inference attacks? It's actually very simple. Our model, similar to the meme on the screen, performs similarly on the seen versus unseen samples, where it can very well recognize the seen samples while it fails miserably for the unseen samples. For our datasets, we choose VoxCeleb because it's one of the best for training speaker recognition models. We only use VoxCeleb 1 due to its small size. The data splits that we use are utterance level, speaker level, and recording level. In utterance level, any recording can be chopped up into multiple pieces and it can be passed into the model. For speaker level, we subset the data for unique speakers, and at recording level, there can be multiple speakers, but the chunks will be complete recordings as a whole. Unfortunately, the recording level dataset was very sparse, hence we did not proceed further with its analysis.
So for the white box attack, we use confidence that the model expresses in a sample as the metric to determine whether or not it is present in the training set. So if the model is trained on a particular sample, it'll have higher confidence, whereas if it has not seen the sample, it will have lower confidence. For the black box attack, we take an original audio recording and add noise and other augmentations to it to change it a little so that the embeddings that you get in the end are different. But if a model has already seen a sample in its training set, then this distance between the embeddings it gets in the original and augmented sample will be lesser than that for samples that it has not seen. Hence, the pairwise cosine distance is what we use to determine whether or not a model has seen a training sample or not. So let's move on to results. So as you can see, the speaker level results are fairly good. This is because a model expresses higher confidence in a speaker it has seen in its training sample and a lower confidence for a speaker that it has not seen. However, for utterance level, the model does not perform as well. Let's see why. Now, the reason it does not perform well is that if a model has already seen a speaker, the confidence it expresses in seen and unseen utterance samples is very similar. Hence, the data that we get is not separable. So that's why we struggle in classifying utterances.
Now I will introduce results on black box attacks. For the black box attack based on data augmentation, both models fail in the speaker level. The accuracy is only around 50% because there is less information about whether the model has seen the speaker or not, compared to the white box attack where we know how confident the model is when classifying the samples. In terms of the utterance level attacks, it is not surprising that they also fail because it is a harder problem than the speaker level attack. To visualize when we can separate seen and unseen samples, we plot a histogram of the cosine similarity score for them. It is clear that it is not possible to separate these two classes with only this metric. In conclusion, we implemented one white box and one black box membership inference attack against speaker recognition models. The white box attacks works better for the speaker level, but not for the utterance level, because confidences are not separable between seen speakers, but separable between seen and unseen speakers. And the black box attack has less information than the white box attack, so it fails on both levels. And thank you for your attention.